cloud. Okay. Yes. Okay. All right. So outlook for the next couple of weeks. We just have 2 more weeks left, essentially. So 4 more lecture days. This week, we are all completing ELC, which is the electrochemistry lab. It is conducted online in that Matt will spend about an hour just lecturing at you how to do the calculations and all that via a Zoom room. That link is on the overview page, right? And so since this is a digital lab, it means that you're not going into the actual lab space anymore. You're done with the lab space forever. So we'll be giving you fake data to fill in your lab notebook pages. So yes, even though we're giving you fake data, you still have to fill out your lab notebook as if you did the lab in class or in the lab space, because we're scientists. So if you don't write it down in your notebook, technically you didn't do it. So you do have to transfer that data into your physical lab notebook, scan it in like normal, and then do the post-lab stuff. So the post-lab does not have a smart worksheets, but it does have this new thing called a presentation of data, which you already kind of did a little bit of that in LCP, that there was this presentation of data PDF template thing. Do you recall that? There's another one of those for this last lab, ELC. So just keep that in mind. And yeah, that's ELC. So Matt will be there to help you with the calculations. I would say it's a pretty calculation heavy lab, that there's a lot of places to go wrong there. So I really wish we could have done this lab in this space. So I'll show a lot of demos here after we finish chapter 12 and chapter 13. So I do anticipate we'll finish chapter 13 probably next week on Tuesday. If there's any time left, I might just jump back to chapter 8, that first part, solids. I might just jump back to that to talk about solids and intermolecular forces and solids a little bit. But the last day of lecture, I will plan to devote towards review for the final, because our final is cumulative. Right, so that last Thursday we will do review. I still plan on doing a final exam review session. Right now, I would earmark it. It's going to be Tuesday, reading day. This will be my review session. I think the date is 4/25. All right, will be my review session, and I believe I have McPherson 1045 booked from 3 to 5. I think that's what it is. All right, so I'll put in an announcement. I'll make a packet for that review session for reading day, because our final exam is actually on Wednesday at, does anyone know the time? 2 p.m. on Wednesday. So that kind of sucks. It's the first day of finals, but hey, then it's out of the way, right? It's out of the way. Okay. All right. So any questions on the outlook for the last couple days? No. We'll be sending out a couple surveys here in terms of lab, and one of the last, I'm going to make another, course design survey for you guys to fill out to get your feedback in the next coming days. And I'll make an announcement about final due dates for things, because as you know, like homework, I do have a late policy for homework. There are certain things that you can upload late in terms of lab. And so I will post all of those due dates to make all of that transparent for you. But if you've been keeping on top of everything, then you have nothing to worry about. All right. Okay. So let's finish chapter 12. Chapter 12 is really long. It has 3 homework sets, and we've been talking about K, big K, for a really long time. Just to put it into perspective, this chapter 12 in this class is 3 chapters in Chem 1220. It's so big, they have to spread this topic out over 2 midterms. But we are just covering it in 1 chapter. So I'm only teaching you guys like the best parts of it, most important parts. So we just finished calculating pHs of strong acids, strong bases, weak acids, and weak bases. So I think that's enough information for you guys as engineers to have under your belt, understanding pH scales. All right, when we're talking about H+ and OH- concentrations, they're rather small. I'm lazy. I don't like to write small numbers. So that's why we use the pH scale. So if we're working with really, really small numbers, like times 10 to the -7 or whatever, if you take the negative log of that number, you get nice big round numbers. So, you know, pH or negative log of 1 times 10 to the -7 is pH 7, where you take the negative log to turn it into the P scale. If you want to undo a pH, you take 10 to the negative pH, all right? So those are H+ concentrations. We can do the same thing with OH- concentrations because both of those substances exist in any aqueous solution. Water is composed of H+ and hydroxide, and both of those ions exist via the self-ionization of water, or Kw. And that has a constant 1 times 10 to the -14. This is K, the equilibrium constant for the self-dissociation of water. And this is true at 25 degrees. And so we see pH and pOH are related by this 14 factor. So the idea is, well, where does that 14 come from? It comes from Kw. Right. So understanding this square and navigating this square is important. I think the most important thing to pull out of this chapter, and how to use ice tables. All right. And so that's what we talked about last week. So moving on to the last part of this chapter is to connect K to a topic we already talked about, which was Gibbs free energy, spontaneous reactions. So let's remind ourselves, what sign of delta G do we want if we want a reaction to be spontaneous? Negative, yes. So typically when reactions are spontaneous, we have negative delta G values. Okay, the reaction goes towards the products. We'll have something that looks like this. All right. So in this example, this is like a weak acid equilibrium where this weak acid dissociates into its H+ and A-, depending how acidic a substance is. Okay, as the acidity of HA increases, Ka increases, we see this difference in energy of reactants and products. When your products are really stable, typically you have a very acidic acid. And that's based upon Gibbs free energy. See, the energy, free energy is decreasing, your products are stable, you have a very stable A- conjugate base, therefore you make a lot of acid, free acid that goes to your pH. So all these ideas are related to one another. You know, what is the extent of the reactant side and the product side present at equilibrium? It actually has to do with delta G. In general, the more negative the delta G that you have, your K increases. And that kind of makes sense. If your reaction is spontaneous in the forward direction, do you have a lot of reactants or products present? If your reaction is spontaneous in the forward direction, you make a lot of products. So if you have a lot of products, what kind of K value is that? It's a large one. So all of these ideas are related. So a positive delta G is typically related, or sorry, a negative delta G is related to a big K, equilibrium constant. So we can actually also relate equilibrium constant to things we already talked about, like Le Chatelier's principle. So remember how we said, okay, we have a system at equilibrium, you add a product, you add some product, disrupt the equilibrium, which way does the reaction shift? Towards the reactants. Yes, but why? Why? It actually has to do with free energy. So yes, Le Chatelier's principle was like the quick and dirty way to predict, okay, add product, it shifts spontaneously to the reactant side. But delta G is the reason thermodynamically why it shifts to the reactant side. So let's look at a example. Concentration can affect spontaneity. So if we look at Le Chatelier's principle, okay, here's a reaction at equilibrium. Okay, we have N2, H2, and ammonia. I'll tell you that at equilibrium, K is equal to 9. All right. Let's pretend we have 1 molarity of everything, and let's determine, is this at equilibrium? So if we insert 1 molarity for everything into Q, we can compare this to K. So NH3 concentration is 1 molarity. We square it. N2 concentration is 1 molarity. and H2 concentration is 1 molarity, and we cube it. So what is the value of Q? Can you do that math in your head? It is 1. Yes. Okay, great. So let's compare Q to K. K is larger than Q. So let's just go back to like the beginning of the chapter ideas. If everything's 1 molarity and we calculate Q as 1, which way does the reaction have to go in order to establish equilibrium? Remember, K is generally, okay, like just very generally, products over reactants. So if Q, the conditions we're actually at, is less than K, and that's my ideal concentration ratio, which way do I have to shift to achieve equilibrium? I like to think Q, it's products over reactants. So I have too much what right now? If Q is small, I have too much reactants, right? Reactants is a big number. It's making it smaller than K. Okay, if I have too much reactants, what does that mean? Which way does my equilibrium have to shift? To the product side. Yeah, because if I consume reactants, make products, shouldn't Q increase in its value until it achieves K? So to me, it sounds like the forward reaction is spontaneous. So relate that to delta G. If the forward reaction is spontaneous, what must the sign of delta G be? Positive, yes. Or sorry, negative. Yeah, so negative. So here we're relating this idea to something we already know. Q is less than K. Spontaneous, the reaction is spontaneous in the forward direction. So that means delta G must be negative. That's the new idea. Let's say if it was the other way, we had Q conditions where Q was greater than K. That means you have too much product. So the reverse reaction has to be spontaneous. So that means delta G has to be a positive number. So there are the new ideas. So let's actually calculate these delta G values at non-standard conditions. And that's this new idea. So, we talked about delta G's before. Sometimes the not is there, sometimes it's not. So there is a distinction. The delta G with the not means at standard conditions. Typically, you can look up table values to get this delta G value, right? Products minus reactants, whatever. And then you can calculate K at those standard conditions. And so understanding numerically how this works, if delta G is a negative value, it means the reaction is spontaneous. Typically, you have large K values are related to very negative delta G values, meaning that the forward reaction is spontaneous. You're gonna make a lot of product. Versus small K values, we typically have. So remember, these are from table values, okay? Standard conditions. Delta G without the not means non-standard conditions, non-standard. So that means we have to use Q. All right, table non-standard conditions, typically we're talking about non-equilibrium conditions as well. So we can calculate Q given certain concentrations that are given for a reaction. And just like we said before, when we compared Q and K to one another and we could predict which way the reaction shifts, the sign of delta G is going to reflect that conclusion that we make. So all of this is related. So I want to show you numerically, all right, using thermodynamics, why when we add a reactant, the forward reaction is spontaneous. It all has to do with delta G. All right, so let's actually do a calculation. All right, so I want you to think about, okay, we have two equations that involve delta G. Which one do we use when? All right, so I have them numbered there. So I give you the KSP, so the solubility product of calcium hydroxide. So let's remind ourselves what KSP is. You take the solid, it breaks up into its ions. All right, so there's two hydroxides. So KSP is equal, I'll write this, KSP, the K expression is equal to products over reactants. So concentration of calcium 2+ times concentration of hydroxide minus at equilibrium squared. All right. So if we know the concentrations of calcium and hydroxide for a saturated solution, we could calculate KSP. But I give it to you. I give you the value of KSP. It's right there. 6.5 times 10 to the negative 6. So I'm asking with this information, what is delta G naught for a saturated solution of calcium hydroxide at this temperature? So look at the equations that I give you. And the question I ask, which equation do we want to use? 1 or 2? 1 or 2? Number 1. Yeah, for a couple reasons. I am literally asking for delta G naught. So that's the one that has delta G naught in it. Also, look at the other information. I give you K. I give you K. Look, I can shove K in there. I didn't give you Q. I gave you K. So we're going to use equation number 1 here and just plug those numbers in. R, right? G is a energy term, so we want to use the energy version of R. So 8.314 joule mole Kelvin times the temperature, 298 Kelvin, times natural log of K, which I give you is 6.5 times 10 to the negative 6. All right, and so that will be delta G in the unit of joules. So you'll get something like positive 29.6 times 10 to the 3 joules per mole, or 29.6 kilojoules per mole. Right, and so we can see all of this kind of come together. K is a really small number. Calcium hydroxide is not very soluble in water. The forward reaction doesn't happen. We can see that K is really small. So if the forward reaction is not very spontaneous, delta G is going to be a very positive number. It's not going to be a negative number because the forward reaction isn't spontaneous. So those ideas are related. All right. So this is for a saturated solution of calcium hydroxide. We got our delta G value right there. Oh, sorry, delta G naught. So based upon the next question. So let's say we have a saturated solution of calcium hydroxide and we add some calcium 2+ to it. We add some calcium 2+ to the solution. We've disrupted the equilibrium. Are we at equilibrium anymore if we add the moment we add calcium 2+? Are we at equilibrium? No. We've disrupted it. We've disrupted K. So what changes about this reaction if we add some calcium 2+? Does delta G not change? Does delta G change? Does both change or does neither change? What do we think? Okay, yeah. So this one's tricky, all right? So if this was Le Chatelier, we would be thinking, oh, you just produced a Q. All right, you produced new concentrations that are not at equilibrium. So look at the equation. If we know the concentration of calcium 2+ added, we have a Q value. What we actually change is delta G. We change that delta G value. But do we actually change the delta G naught value? No, we don't change the table value at all. That still remains the same. We calculated it. And so that will propagate itself and we'll compare it to the Q values that we get later. So basically these delta G values, again, non-equilibrium conditions, Q conditions. And that's what the next question is saying. It's saying, hey, now let me give you Q conditions and predict what's going to happen. All right. So let's say you make up a solution that is this concentration of calcium, that concentration of hydroxide. What is delta G for this reaction? So if we're calculating delta G, what equation are we going to use? The first one or the second one? The second one this time, because the naught is very important here, whether it's present or not. So we actually want to calculate Q in order to use that second equation. We actually already have delta G naught. We already calculated that before. So if we just get Q, we can plug everything in. So Q comes from our KSP equation, but we're just using non-equilibrium conditions. So calcium 2+ times hydroxide squared. So I thankfully gave you these values. So 0.005 molarity times hydroxide, 0.05 molarity, and that is squared. So we see that Q at these conditions is something like 1 times 1.25 times 10 to the negative 5. Okay, So remember how we compared Q and K for our ammonia reaction on the last slide? Let's compare Q and K again. Q is what compared to K? It's larger. So what does that mean? Which way does our reaction have to shift if Q is bigger than K? You have too much what right now? Product. So your reaction has to go in reverse. So before we even calculate G, if the reverse reaction is spontaneous, what should the sign be of delta G? Positive. If not because the forward reaction is spontaneous if delta G is negative. So if we want the reverse to be spontaneous, that's a positive delta G. So let's actually calculate it, all right? And see if it matches our intuition. So Q, we got Q, so we just plug and chug. Delta G is equal to delta G naught. So we already calculated that, 29.6 times 10 to the 3 joule per mole, plus RT ln Q. So 8.314 times 298 times natural log of Q that we just got, 1.25 times 10 to the negative 5. All right. And so we get that this term, if you calculate it, 298 times natural log 1.25 e negative 5. Okay, we got negative 27971. And so if we subtract these numbers, you get something like minus 27971. You get positive 1.63 times 10 to the 3 joules per mole. So is delta G positive? Yes, it is. So if delta G is positive, that means the forward reaction is not spontaneous. It means that the reverse reaction is spontaneous. And that's what our Q versus K predicted. Delta G, whoops, sorry. Okay, crap, where did I go? Delta G is positive, and this is consistent with a Q is greater than K. Right, so this is where the reverse reaction is spontaneous. So what should be observed? We should see solid precipitate out. Okay, so calcium hydroxide should precipitate out of solution. That's what's going to happen. All right, so let's say one more condition. A solution is made up, so the KSP, or the Q, is equal to 6.5 times 10 to the 6. What is delta G for this reaction? So I just give you what Q is. All right, so let's just do the math again and put 6.5 times 10 to the negative 6 into that Q spot and see what we get. So 29.6 times 10 to the 3 joules per mole, 8.314, 298, natural log 6.5 times 10 to the negative 6. Someone put that into their calculator and see what you get. E3 plus 8.314 times 298 times ln of 6.5 e to the negative 6. So you get a really tiny number, all right? So 0.6 kilojoules per mole. So here are conditions where Q is actually equal to K. What does that mean in terms of Le Chatelier's principle? You're at equilibrium. So is the forward reaction spontaneous at equilibrium? Is the reverse reaction spontaneous at equilibrium? Actually, both of them are. So at those conditions, delta G is actually equal to 0 in this case. So the number that we calculated here, it's basically really close to 0. And what I'm trying to get you to come to the conclusion is that since we're at equilibrium, Q is equal to K, there is no driving force for the forward or the reverse reaction to happen. Delta G is 0. We're at equilibrium. The reaction is going to stay the same in terms of concentration and shifting. All right. So that's putting all of these things together. That's how we do it mathematically, but let's just do it conceptually now. All right. Let's just conceptually think about delta G and does it increase or decrease given these changes? And so do remember these two equations and how we calculate delta G given non-equilibrium conditions. So let's say we take these two reactions and we increase the concentration of H2. What does Le Chatelier's principle predict for this first reaction? Which way does the reaction shift? To the, yeah. Feel like we're good at this now. It's like, oh, you add reactant, it's going to go to products. It's going to do the opposite. But the other reaction, if you add H2, where's it going to go? It's going to go to reactants. Okay, great. So if we add H2 and the forward reaction spontaneously pushes the reaction forward, what should the sign of delta G be? It should be a negative value, yes, in order for that to be consistent, where we're saying this forward reaction is in fact spontaneous. But what about the other example? All right, we add H2 as a product, it pushes it to the reactant side. So what should the sign of delta G be here in order for all of that to be consistent? Positive, because a negative delta G means the forward reaction is spontaneous, but since the reverse reaction is spontaneous, that implies a positive delta G. All right. Okay, so how does Q deviate from K the moment H2 is added? So remember, K is generally products over reactants, all right? So if we add H2 at our non-equilibrium conditions, we're increasing the concentration of products. So Q should be less than K at that moment. We add H2 because H2 is a reactant. So we're making the denominator a bigger number, right? And so the last one here, if we add H2, the moment we add H2, we're adding a product. So we're making the numerator a bigger number. So Q is actually larger than K at that moment. And so this is finally conceptually what ties in all the ideas of K equilibrium, Le Chatelier's principle, the reaction quotient, and free energy all together. Okay, so all of those, quick and dirty ways that we predicted shift using Le Chatelier's, you were actually predicting the sign of delta G when you were doing that. All right, so all of that comes together there. So this is more conceptual, this slide, but it has the exact same conclusion as what we did mathematically up here. All right, so we will do one more example, two more examples on equilibrium and free energy. And so we're going to study the equilibrium constant for this reaction, specifically the Kp, so the pressure term of the equilibrium constant for this reaction. So let's calculate the equilibrium pressure of CO2 of this reaction at standard conditions. So 298 Kelvin, blah, blah, blah. All right, so the first idea here is since we're studying equilibrium constant, what is the equilibrium constant expression for this reaction for gases? Because it's Kp. It's products over reactants, but what species go into K? Does lead oxide go into K? No, because does a solid have a pressure? No. So that means lead oxide does not go into K. But does CO2 go into K? Heck yes, it does. So Kp is equal to pressure of CO2. Do we put the reactant in here in K as well? No, because it's a solid. So it looks like if we calculate K, we actually know the equilibrium pressure of CO2. So that's pretty cool. All right. So if we want to calculate the equilibrium pressure of CO2, which is K. So essentially what we're doing is calculating K at standard conditions. What equation should we use here? 1, 2, or 3? What variables do we have? We have standard conditions. I want to calculate K. And look, I have a bunch of thermodynamic data. Which equation should we use? We should use that first equation, because here I'm relating delta G to a K value, and that's what I want, specifically Kp in this example. And so I've done the work for you of getting delta G of this reaction, but remember, you can do it yourself, where you just do products minus reactants. You can get all those values too. I just got it for you. So this example is straightforward in that we take this delta G value, because this is at standard conditions, and we just set that equal to our first equation and calculate K. That K will be equal to the equilibrium pressure of CO2 at equilibrium. So we just plug everything in, but do make sure, because R is in joules, that your delta G is in joules as well. So 43.2 times 10 to the 3 joules per mole is equal to negative 8.314 times, what's my temperature? 298, because it's standard conditions, times ln K, where K is, again, equal to the pressure of CO2. That's my goal. All right, so we're just solving for whatever's in that natural log. All right, and so what you get is, oh, yep, I have the answer right there. All right, so using that thermodynamic data at standard conditions, I can get that K value, partial pressure of CO2 present for this reaction at 298 Kelvin. Great. Okay, so that one's kind of plug and chug. So we actually have enough information on this one slide to predict the equilibrium pressure of CO2 at any temperature, right? Because we have this third equation that we talked about in chapter, I forget what chapter, entropy, was that the previous chapter? I don't remember. I don't remember. Okay, I'm having a brain fart here. So do you recall us calculating delta G values at different temperatures, where we assumed that delta H and delta S stay constant at all temperatures? And so we can calculate delta G at a varying number of temperatures. So we're going to do that exactly again, right? So let's actually calculate the equilibrium pressure of CO2 for this reaction, not at standard conditions, but this time at 473 Kelvin. All right, so recall delta G changes with temperature. So can I use this table value delta G reaction at 200 degrees Celsius? No, I can't. I have to get a new delta G value. And so to do that, I'm going to use this third equation. I'm going to get the new delta G value using the delta H and the delta S that are given. All right, but just at the new temperature, to 200 degrees Celsius or 473 Kelvin. So the idea here, I want that new delta G at 473 Kelvin. So I'm going to use delta G equals delta H minus T delta S instead. So do make sure that these units match. So I'm going to do 88.3 times 10 to the 3 joules per mole, that's delta H, minus T, so this is at 473 Kelvin, times delta S, so times 151.3 joule per mole Kelvin. Oh, there should be a Kelvin there, sorry. What happens when I copy and paste things? Okay, so you plug all those numbers in and you get this new delta G value at 473 Kelvin. We'll see it's a little bit different. Did I calculate that? Yes, it is equal to 16.73 times 10 to the 3 joule per mole. So there's my new delta G value. It's a little bit different than the delta G value at standard conditions, but that makes sense because this is at a different temperature. So this isn't our answer. This isn't our answer. We actually want the equilibrium pressure of CO2 at that temperature. Delta G is just a way for us to get there. So now this is where we can use that first equation. Now that we have delta G, we can just plug in that delta G to calculate K at this new temperature. Make sure using the appropriate T in the equation then. So putting it all together, we do 16.73 times 10 to the 3. That's delta G equals negative R 8.314. Temperature, so this is 473 Kelvin times ln K, and this is the K that we're solving for, that is related to the equilibrium pressure at this temperature of CO2. Right, so what the big idea here is that we got a different delta G value from delta H and delta S, because delta G does in fact change with temperatures. All right, and we were able now to take this idea one step further. We actually did this question before in chapter entropy, but I had you calculate delta G. So now we're just taking it one step further and calculating K based upon those delta G values. Because to me, a K value has much more information embedded in it. It tells you relative concentrations of things. Those are things we can measure. Delta G, not so much. Like, yeah, I understand positive, negative, but a K equilibrium constant is a much more valuable information to us than just delta G that we learned about previously in that other chapter. All right, so that is equilibrium. That's it. So homework is due on Monday for that last set. The first two sets for this chapter were already due on Monday. So this one, yeah, yesterday. So this last one will be due next week. Good. Okay. And just kind of some closing remarks about homework. So there's, after this homework set, electrochemistry, our last homework set, only has 2 sets in it. And that's it. That's all, everything for homework. So if you recall the grading policy for homework, do you remember the grading policy? No, you just do everything on time and complete, right? Yes. So there is a late policy on homework. Did you know that? If you don't submit, when's our due date for everything? Monday at 6 p.m. Yes. If you don't hit submit at 6 p.m., you can still complete the homework assignment. If you complete it, all of it, and hit submit now, you can still get 50% of the credit. All right. But I'm going to make a hard cutoff date of when I'm going to allow those late homeworks. And so it'll be on reading day, essentially reading day at midnight. And I'll make the announcement, is the last day to submit late homework assignments. So there should not be any dashes in the grade book for any homework assignment, right? Because if you didn't complete it, you can always complete it for completion and get 50% of the points. I mean, some points are better than nothing, and you're learning at the same time, right? So if you have any missing homework assignments, they can still, even if it's chapter one, you can complete it for partial credit. Okay. Yes. And I do see some just missing sporadically homework assignments. So yeah, you can still complete it even now. Okay. Yes. All right. So that is chemical equilibrium. That is midterm 2 and half of midterm 3 for 1220 that you just covered. We covered in a week and a half. All right. So this is the last chapter. This is my favorite chapter, electrochemistry, because we do cool demos, and I think it relates to real life a lot, whether you like it or not. So electrochemistry, this is our last chapter. We're going to bring back ideas of spontaneity. Why do batteries, why are they spontaneous? Why do batteries die? It's because they're non-spontaneous at that point. Yeah, and other things like that. Okay. There's a couple of things that you should review. Reactions happening in aqueous conditions, net ionic equations. That was back in chapter 3. All right, where we have ionic stuff dissolved in water. And then I would just memorize this. Okay. NOx red cat, where NOx stands for anode oxidation, and red cat stands for reduction at the cathode. Some people go with oil rig. Do you know what that stands for? Okay, oil rig stands for, okay, we'll just write them all out. NOx, anode, cathode, okay. Red cat, reduction, cathode. Oh wait, what am I doing? I don't know what I'm doing. Brain fart. Okay, reduction, cathode. There we go. All right. Anode oxidation. That's what I meant. Okay, that's that first one. Was that a LaCroix? No. Okay, great. All right. So that's NOx red cat. Oil rig stands for oxidation is loss of electrons, I think. I think that's what it stands for. And then reduction is gain of electrons. I don't really like that one. I like Leo goes grr. Leo goes grr. What does that stand for? Loss. Lose electron. Oh, I said loss, whatever. Okay, I'm just speaking in past tense. Loss of electrons is oxidation. Gain of electrons is reduction. So oil rig and Leo goes grr are based, they're saying the same thing. Just whatever way you want to memorize that. Okay. But we're going to be using it so much that you're just going to memorize it. All right. So, all right, we'll talk about redox reactions, spontaneous cells, essentially batteries. Our book calls them galvanic cells. In other textbooks or on the street, you might hear them be called voltaic cells. It means the same thing. Galvanic cell, a voltaic cell. In both cases, it just means that the cell potential is a positive number. That's all it means, meaning that it's a spontaneous electrochemical cell. We'll talk about cell potentials, so how to actually calculate E cell. We'll talk about cell potentials and equilibrium, that's big K. So cell potentials that we measure is in fact related to chemical equilibrium. We'll talk about batteries, which a battery is essentially a galvanic cell. And then we'll talk about electrolysis and stoichiometry. All right, okay. And so here are some of the ideas. We'll talk about batteries, voltaic or galvanic cells here, and then this demo that children love to see because they think potatoes contain energy. They're like, ooh, potatoes, they contain electrons or whatever, and we can harvest the electrons from potatoes. So we could solve the world energy crisis by just potatoes, obviously, right? But the piece of information that's kind of hidden in this picture is the components of these screws. Okay, you can't just use any screws. I think one's galvanized and one's like an iron screw. And so essentially what's happening here is a redox reaction, but you see children are stupid. So they think that the electrons are coming from the potatoes, but the electrons are in fact coming from the screws themselves. All right, so yes. Okay, has anyone seen that demo? Yeah, it's not the potatoes, it's the screws. All right, so let's do a little bit of review. Can you answer this? You should be able to. What is the net ionic equation for this reaction? Can we do that? The net ionic equation. So remember, net ionic means, so this is happening in water. We want to think about what do these species actually look like in water. All right, so let's see if we can't come up with this. Remember, with net ionic equations, we have to split stuff up. We got to split our strong electrolytes. Strong electrolytes. All right, and then we remove spectator ions, and that's how we get our net ionic equation. So do we split copper solid in a net ionic equation? Think about what that looks like when it's dissolved in water. Well, one, does copper solid dissolve in water? No, so we no split that, no split. Okay, do we split silver nitrate? Yes, because silver nitrate is a strong electrolyte. It is going to split up into silver plus ions and nitrate anions. So yes, split. So split that guy. Okay, do we split silver solid? No split. No split. Okay, do we split up copper nitrate? Yes, because it's a ionic compound. It's a strong electrolyte. So we yes split that. So let's write everything out again. So we got copper solid. We split up our silver nitrates, but there's two of them. So we get 2 silver pluses, 2 nitrates minuses, arrow, 2 silvers, solids that aren't split. Then we get a copper 2 plus, and then we get 2 nitrates minus. Okay. Is that my net ionic equation? No, because what I got to do, I got to remove spectators. Where's my spectators? Nitrates, yes. So I can remove those. And then we see that this simplifies to copper solid plus 2 silvers gives us two silver solids plus copper 2 plus. This really simplifies what reaction is going on. We're turning solid copper, you know what that looks like. It's all brassy and orange or whatever, okay? We are dipping it into a silver solution. It looks like water, whatever. But then as the reaction proceeds, we see that some of that nice copper material starts to what looks like dissolve away because it's being converted to copper 2 plus anion. It's going into solution. We also see silver solid deposited on that piece of copper. So writing the net ionic equation clearly shows you what reaction is happening without these dirty nitrates kind of like floating around and like distracting you with what's happening. And what's nice here is when we have the net ionic equation, we can clearly see oxidation numbers to figure out what is being oxidized and reduced. And so that's the next part of this chapter. What's being oxidized, what's being reduced, does this reaction happen spontaneously? Those are all the things that we're going to predict. So let's go over oxidation numbers so we can figure out what atoms are being oxidized and reduced. It's not that bad, all right? So once, especially if you have your net ionic equation, if you have that and you can think about charges and think about how a substance goes from reactants to products and how its charge changes. Because that will tell you whether electrons are either given off or absorbed in a reaction, all right? So oxidation numbers very closely similar to charge. So here are the rules with oxidation numbers. The oxidation number of any element in its elemental form is always 0. Like look at all of these like elements, they have a charge of 0, right? So like oxygen gas, hydrogen gas, iron solid, aluminum solid, bromine liquid. Let me think of some other ones. Copper solid also has an oxidation number of 0. Silver solid, all of those things. Okay, 0 oxidation number. Versus things that are ionic. If something's ionic and it has a charge, that's its oxidation number for that element. So for example, instead of silver solid, what if we had silver plus cation? That's a +1 charge. What is its oxidation number? It's +1. So oxidation number is just related to charge, essentially. What about zinc 2 plus? Its oxidation number is +2. What about iron 3 plus? +3. What about chloride minus? -1. So keeping track of charges will help us figure out what's oxidized and reduced. And so here are some like tips to figure out oxidation number. Sum of oxidation numbers of all the atoms always equals the charge. So for example, iron in iron chloride must be +3. Each of the chlorides are -1 oxidation numbers, because then when you add them up, that charge equals 0. But for something like nitrate, oxygen has a -2 oxidation number. That's actually tip number 4. So I'm kind of jumping ahead here, but there's 3 oxygens present. So total oxygen is giving a -6 charge. So we can actually back calculate what nitrogen must be in order for all of those oxidation numbers to add up appropriately. Nitrogen must be +5, because then that adds up to the overall charge of the molecule, or the ion in this case, nitrate, which is -1. All right, and so the trick that I used right here, where I knew oxygen is -2, it's just kind of a rule that you follow. Oxygen in our class is almost always a -2 oxidation state, except in oxygen gas because it's 0 there. And then hydrogen is almost always +1 in this class, except in hydrogen gas. All right, and with that tip, you'll be able to figure out the oxidation number of anything. All right, if we know what oxygen is, because oxygen is oftentimes involved in redox reactions. So in our class, it's almost always +1 when it's attached to a non-metal. So like something like CH4 or even HCl. Those all have a +1 oxidation number of hydrogen. An example where hydrogen has a -1 oxidation number, this isn't very common. This is for hydrides. This would be something like lithium hydride. And that's not common. So not for this class, but that's something you might encounter. And then of course, hydrogen gas, that has a 0 oxidation number. If you just think charge, you'll be fine. So let's think charge. Let's assign oxidation numbers. What is oxidation number of hydrogen in H2? 0. What about bromine and Br2? 0. What about H and Br in HBr? So they're both 0, right? Because we just did those. Are they both 0, right? Hydrogen is 0, bromine is 0. They're both 0 in HBr as well. No, they're not, because you can think of HBr as an ionic compound, H plus and Br minus. So in this substance, hydrogen actually has a +1 oxidation number. Bromine, okay, that should be a Br, not a B, is -1. All right, so see how oxidation numbers can change depending on where that element is, where that atom is, what compound it's in. All right. Okay, let's keep thinking charge. So this is kind of like chapter 2 review, sort of. All right, calcium and chloride and calcium chloride. +2 and -1, right? It's just charge, just think charge. Okay, let's get a little harder. Chromium and oxygen in this chromium oxide compound. There's one you already know, and that's oxygen. Oxygen in a compound is almost always -2. So since there's 3 oxygens, each one is -2, so times -2 times 3, that's oxygen is contributing -6. So that means the chromiums have to contribute a +6, but there's 2 chromiums. So that means each chromium is actually contributing how much? +6, or sorry, +3, yes, +3. My hand said 3, but my mouth said 6. Yes, chromium is +3 here. All right, and so then if you want to check yourself, just check that all the charges add up. There's 2 chromiums, each of them are +3, that's +6. There's 3 oxygens, each of them are -2, so -6, that equals 0. Perfect, great. This is like chapter 2 naming review, kind of. All right, manganese and permanganate anion. Is there something we already know? Oxygen. Oxygen has an oxidation number of -2, but how many are there? 4. So I like to think, okay, oxygen is contributing -8. It has to add up to its charge. So what does manganese have to be? +7. Are you thinking charge? Because that'll get you the right answer. Okay, finally, all the atoms in calcium oxalate. What? Yeah, yes, you know oxygens, -2, yes. Okay, 4, there we go. Very good. Do we know calcium? What is calcium always in an ionic compound? We did it up here. +2, yeah, it's +2. This one's no different, okay? And so with that information, you should be able to get what that carbon is, all right? Calcium is +2. We have 2 carbons. And then we have 4 oxygens that are -4, or no, not -4, -2 equals 0. So then you just solve for whatever carbon has to be, all right? Think charge, all right? Can someone solve that for me? It's plus what? 3 plus 3, okay. So carbon's oxidation number in this compound is +3. That's it. Good? Okay, charge. So the rules, think charge, all right? Back from, chapter 2, oxygen is typically -2 in a compound. Hydrogen is usually +1, and then you're good to go. Okay, all right. So can we go back to the reaction? Yes, all right. So if we can track oxidation numbers, we can determine what is being oxidized and what is being reduced. So here are definitions. A substance is oxidized when it loses electrons. I like to think a substance is oxidized if its oxidation number goes up. Right? Because if you go from something like +1 to +2, in order to achieve that, you have to lose an electron, got to shed one off to go up in charge, right? So that's loss of electrons. So what is that, Leo? That's Leo. And then the reduction part, that's the GR part. A substance is reduced when it gains electrons. So how does its oxidation number change? in a reaction? It's going to go down. Yes, oxidation, reduction. You're adding electrons. So that oxidation number, that charge is going to go down generally. All right. And so that is reduction. So we have to be careful with our language here. I can say a substance is oxidized, a substance is reduced. I can identify a substance as a oxidizing agent or a reducing agent. So the substance that's oxidized is also called the reducing agent because it gives up the electrons to feed the reduction reaction. The substance that is reduced is also called the oxidizing agent because it's what's stealing the electrons to oxidize the other thing. So we have to be careful with language here. So let's go back to this example. Here's our net ionic equation that we already did. My strategy is I get the oxidation numbers of everything, and then I just track. So this one should be easy because we have the net ionic equation already. What's the oxidation number of copper solid? 0. What about silver plus? +1. So just look at the one atom. Okay. What about silver solid? 0 and copper 2 plus +2. Perfect. So now we just track those oxidation numbers. Copper is going from 0 to 2. Silver is going from +1 to 0. So we see one of the sets goes up, one goes down in oxidation number. And so we can use our definitions. Copper is going from 0 to 2, +2. So what is copper being done? What's it doing? Is it being oxidized or reduced? Oxidized. Yes, it's being oxidized. So here it's copper solid is being oxidized. And then let's look at silver plus. Silver plus, its oxidation number is going down. It's being, the number is being reduced. It's going down. So we see that silver plus is being reduced to a 0 oxidation number. It's being reduced. Okay. So here are ways to check yourself. All right. If you get all the oxidation numbers and you see all of everything goes up, all the oxidation numbers goes up, like everything's being oxidized, that's impossible. Okay, for a redox reaction to occur, so redox stands for reduction, oxidation. Both of those have to happen at the same time. Something needs to be reduced, something needs to be oxidized. We can't have two things that are being oxidized or two things being reduced. So if you go through this process and you see, oh, everything increases in oxidation number, you screwed up and you should try again. Okay, something has to be oxidized, something needs to be reduced. All right, so based upon our answers here, what's the oxidizing agent? What's the reducing agent? Yes, we swap them. So the reducing agent, the thing that's doing the reducing, so giving up electrons, is going to be copper solid, and the oxidizing agent, the thing that's robbing electrons, is silver plus. Okay. All right. So that's useful if we already have a balanced redox reaction given. Hopefully I can get to the demos here. All right. So let's actually balance redox reactions. It's a little bit more complex than us balancing equations back in chapter 3. Remember when that was such a simpler time? Yes. Look how far you guys come. You're so much more comfortable in lab. You're fearless of burettes and graduated cylinders and volumetric pipettes, but now you never have to use one ever again, probably. No, I lied. I asked my husband if he ever did a titration in industry, and he said yes, he did. He had to do some titration to figure out like the concentration of some polymer, and I was like, oh, cool. Like, did you do this in the titration? Did you use a burette? And he's like, what? No, I just had my technician do it. So he just designed it. He made someone else do it. So anyway, okay. So redox reactions. We have to be cognizant here. So the new thing that we're learning about here are electrons. There are electrons involved in a chemical process. So not only do we have to balance the atoms themselves like we did in chapter 3, right? Like checking like, okay, you know, carbons balance, hydrogens balance, oxygens balance. We need to make sure that the electrons balance as well. And that can be tough because typically electrons, we cancel those out in a chemical reaction. They're kind of being transferred behind the scenes, so they're harder to balance. So that's the idea. Electrons also have to balance in addition to the atoms. So this example is kind of easy, this first one. Zinc goes to zinc 2 plus, H plus goes to H2. So my intuition says, okay, I'm going to put a 2 in front of that H plus. So I make the atoms balance. Okay. And so this reaction is actually now fully balanced. There's 1s in front of everything and a 2 in front of H plus. Here's an example where if I balance the atoms, the electrons are balanced too. Because if you add up the charges here, what's the charge, the total charge on the reactant side? +2, because there's 2 H pluses, and +2 coming from zinc. So in this example, you balance the atoms, the electrons are balanced. And it's easy. But this one's a little harder. Me personally, I can't just look at that and know what the coefficients are. This one's actually a lot more intense. And there's a strategy to balance these harder ones. Me, a mere mortal, cannot just look at that and know how to balance it. I have to go through my 7 steps of balancing a redox reaction in acidic conditions. All right, there's a strategy. If you master the 7 steps, you will always be right. Okay, so just write these down and then we have to go through the steps because I think just me reading this isn't very beneficial. But in essence, we need to, in a redox reaction, we need to think about the oxidation and reduction reactions separately first, balance them separately, and then add them up together at the end, but in a very special way. We split the reactions into 2 half reactions. We balance all the atoms in a certain way, but we also balance the charges. Then when we add up the 2 reactions, we want to make sure that the electrons being produced at oxidation is the same number of electrons being consumed at the reduction reaction. And that's how you balance a redox reaction, right? So on the reduction side, electron should be a reactant, but in oxidation, it's a product. And that's where Leo goes grr comes from, all right? So let's do an example. I think that's easier. Oh, I have the thing there, okay? So what's this balanced redox reaction? So I have the steps here, and I even have the oxidation numbers for you. So I've made it really easy because those oxidation numbers will help you split those half reactions. So cadmium is going from 0 to +2, and nickel is going from +4 to +2. So cadmium is being what? Oxidized because its number is going up, and nickel is being reduced because its oxidation number is going down. All right, so now that we have identified the half reaction, this is where we need to rewrite them and split them up into those half reactions. I like to start with the oxidation reaction first. So we have cadmium solid. So we want to write that substance, the cadmium substance, and then an arrow and point to the other cadmium substance. So this time it's cadmium hydroxide. All right. Yeah, and it's solid, but I'm gonna just ignore phases. All right. And then let's rewrite the reduction reaction as well while we're at it. So we have nickel O2, arrow, nickel hydroxide. All right, so those are my half reactions. They are not balanced. So now let's balance them. The idea here is first, we already split the half reactions. Now we need to balance the atoms. First, balance the other atoms other than oxygen and hydrogen by changing coefficients. So here I see, okay, my cadmiums are balanced, so I don't need to add any coefficients. But let's pretend this was like 2 cadmium, like that. That means you would have to put a 2 coefficient there to make it balanced. Okay, just for example. Next, you balance oxygens by adding waters to the appropriate side. So I see in the oxidation reaction, there's actually 2 oxygens on the product side. So if I add 2 waters on the reactant side, I will match those oxygens. Do you agree? Yes. Okay. But see, now I screwed up. I added water. I made the oxygens balance, but now I screwed up the hydrogens. All right. So how we take care of hydrogens, we balance that last. We balance hydrogens by adding H plus. So here you add water. Now we add H plus. And this is what I mean by balancing in acidic conditions, because we're balancing hydrogens with H plus. So tell me, in that oxidation reaction, where am I going to put H pluses? On which side? Products or reactants? Take inventory. I saw some heads moving on this side, plus H plus, but how many? 2 of them, yes, there you go. Now the atoms are balanced, but are the charges balanced? No. So this is where we want to make sure that the charges on both sides match one another, and this is where we add electrons to do so. So I like to kind of take inventory of the charges. I see that the oxidation side or the reactant side is 0, and then the product side has a total charge of +2. So in my mind, if I add 2 electrons on the product side, I can make everything charge balanced. Good. All right. So we just did one of them. We got to do the same thing for the second one, the same format. Balance the other atoms, which we do. We have 1 nickel on each side. Now we balance oxygens. Are the oxygens balanced? Yes, so we don't have to add any water. Are the hydrogens balanced? No, so let's add H plus. Where are we going to add them? To the reactant side. How many of them? 2 of them. Cool. All right. So now the last thing, the new idea with redox reactions, balance the charge. So again, take inventory. I see that the product side has 0 charge. This is +2. So if I have 2 electrons feeding into the reduction reaction, that makes it all charge balanced. All right, so those are my 2 half reactions. I don't feel like doing that. So to my 2 half reactions, all right? So now we can add them up, but we want to make sure that the number of electrons that come from the oxidation reaction match the number of electrons coming from the reduction reaction. That's the important thing there. All right, so do they match? Yes. So if I add up those 2 reactions as is, those electrons will cancel out and you'll never see them. All right. But we know behind the scenes that this reaction involves 2 electrons being transferred. That's behind the scenes, but because it ends up canceling out. So when we add these 2 things up, do make sure you cancel appropriate things. So the 2 electrons cancel. Is there anything else that cancels when we add up these 2 reactions? The H pluses. The H pluses will cancel as well. So the full balanced equation is 2 waters plus cadmium solid plus nickel oxide, arrow, cadmium hydroxide plus nickel hydroxide. I think this is the reaction in a nickel cadmium battery, I think. Right? So there's our full balanced reaction. So tell me, what substance is being oxidized? We technically didn't need the full balanced reaction to do that. We can actually just look at how we assigned oxidation numbers. Cadmium is going from 0 to 2 plus. So it's cadmium solid is being oxidized. So that means nickel oxide is being reduced. And then we just swap them. The oxidizing agent is the thing that's reduced. So nickel oxide is the oxidizing agent and cadmium is the reducing agent. There we go. And then finally, how many electrons are involved in this redox reaction? It is 2, because behind the scenes, we cancel out 2 electrons in balancing the half reaction. But you actually don't need, there's a trick. You don't actually need to do the whole balancing half reactions to get this value. You can really just look at the oxidation numbers as well. If you look at how the oxidation numbers of cadmium are changing, it's going from 0 to 2. How many electrons are required to make that happen? 2. Also, you can look at nickel. Nickel is going from +4 to +2. How many electrons do you need to make that happen? 2. Yeah, so you can also get the number of electrons involved looking at the balanced reaction, or not the balanced reaction, just the half reactions as well. All right, so let's do a harder one, then I'll do my demo. Okay, so actually, before I do that, okay, if this is a spontaneous reaction, the reaction spontaneously goes left to right, this reaction generates electrons, right? It generates a cell potential, and we can measure that cell potential. We can look at table values to measure that cell potential. You can put a multimeter on that. So I just have a different spontaneous cell, all right, where we are oxidizing and reducing something else. I just wanted to show this. All right. So if a cell potential is spontaneous, you'll get a positive cell potential when you set up your voltaic cell. So here I have copper and zinc sitting in solutions of copper nitrate and zinc nitrate. So this is a spontaneous cell. And if that I connect these electrodes here, all right, we do measure a non-zero cell potential. So right now you read that it says negative 1.1 volts. And we'll actually calculate this here soon. And so the idea is, well, why does it say negative? I thought you said that this is a spontaneous cell. See, electrons are stupid. They don't care about polarity. They'll just run through the circuit whichever old way it wants to. So that's why it's showing a negative sign. So if I swap these two leads, electrons will only flow in one direction, only in the spontaneous direction. So right now it's flowing through this multimeter in a way where the polarity is negative. So if I swap these two leads, I should read the same potential value that we can calculate from table values, but it is just a positive number. So can someone read that? What does it say? 1.1, but it's positive. There you go. And we will calculate this. We'll calculate this here soon. The cell potential between copper and zinc at standard conditions is 1.1 volts. So the cool thing, we are reading 1.1 volts because electrons are spontaneously going from this this side of our cell to another side of the cell, and it's going through the multimeter. Right, electrons are passing through it because it's the path of least resistance. I'll give you, I'll be honest, electrons scare me. Electricity scares me. It's one of the things I'm scared of because I can't see them, and current can kill you. So yeah, I've been shocked a number of times, and I still don't understand electricity. All right, so electrons are flowing from one side to the other. So what if I give the electrons a different path? Instead of putting them through a multimeter, let's make it do something cool. I should have done this at the beginning of the class. Yes. So here's my thing. I'm going to just give the electrons a different path to take. All right, different path to take. Boom. Okay, so there we go. I'm just giving the electrons a different path to go through. Okay. Yes, I should have made it go the whole class. All right, I have 7 minutes. We have 7 minutes, or I guess 5 minutes to balance this redox reaction, and then I have another demo. So let's consider this redox reaction between permanganate and oxalate and balance it. All right. What do you think would happen if I would switch the leads? Would it stop? It would, yeah, it would just spin the opposite way because electrons are stupid. So unless we had a like PN junction that would only let electrons, some type of like polarity safety switch that wouldn't let the electrons flow the other way, then maybe nothing would happen. But because electrons are stupid, it would just spin the other way. Okay, so let's balance this. Okay, so in acidic conditions, so the same steps. Let's get our oxidation numbers. Manganese is +7. Carbon, I think we already did oxalate, didn't we? That carbon was +3. We already did that in the previous slide, and manganese was +7. Manganese 2+ has what? Oxidation number? +2. Whoop, +2. And then carbon and CO2 has what oxidation number? Plus oxygen is -2. There's 2 of them, so carbon has to be +4. Cool. All right, so let's track those babies. There we go. +7 to +2, 3 to 4. So manganese is being what? Reduced. Carbon in oxalate is being oxidized. Great. So let's split up those half reactions. I like to start with the anode first, or the oxidation reaction first. So oxalate goes to CO2. So we need to balance the atoms first. So we put a 2 coefficient in front of CO2. What do we balance next? Oxygens by adding water. So we add 2 waters to the product side. So there's 4 oxygens on each side. And now we add what? H pluses. So I'm going to add 4 H pluses to make all of that balanced. Great. Now the hard part is doing electrons. So I like to take inventory. There's -2 and +4. So there's a total of +2 on the reactant side, 0 on the product side. So if I have, oh, did I mess up? What did I, oh no. Oh wait, I messed up. Oh, oxygen was already balanced. I actually didn't need any hydrogens. Okay, wait. CO2, CO4, there we go. Yes, all right. Yeah, that's already balanced. Yes, okay, the atom's already balanced, right? 2 carbons, 4 oxygens. Is that right? Yes. So electrons, I knew I was wrong because when I went to balance, my electrons were on the wrong side. I had them on the reactant side. So I'm like, wait, that's not right. Okay. So there are 2 electrons being given off in this oxidation reaction. Now this is balanced. Okay, great. So that's oxalate. Let's look at the reduction reaction. So manganese. So MnO4 gives us Mn2+. So now I need to add waters. So 4 waters to make the oxygens balance. But now I have too many hydrogens. So I'm going to add 8 H pluses here to make those hydrogens balance. Okay, so now I can take inventory of all of my charges. So +7 on the reactant side, +2 on the product side. So I'm going to put electrons on my reactant side, but how many? 5. Great. So that's my reduction reaction. Great. So can I just add these two? Redox or half reactions as is? Will they cancel? Those electrons cancel? No. We need to multiply both reactions by the least common denominator. No, least common multiple by each other. Well, not necessarily. It's not always by each other. Because what if it was like 2 and 4? Then I would only just multiply this one by 2. So what's the name? Least common multiple. Okay. Yeah. So I'm going to multiply the reduction reaction by 2, the oxidation reaction by 5. So we have new coefficients. I don't want to rewrite them. So I'm just going to rewrite them up top here. 5 oxalates 10 CO2s and 10 electrons. 10 electrons, 16 H pluses, 5 manganeses, or no, that's wrong. Yeah. Okay, 2. 16 H pluses, 2 permanganates, 2 manganeses, and 8 waters. So what we see is all of those electrons cancel. All right. And then I think I have the balanced reaction right there. All right. So when you add those 2 reactions, the electrons cancel, nothing else cancels. We're good. So I want to show you what it means to balance in acidic conditions, because we see in this reaction, acid is required. So let's look at a redox reaction. So we're actually looking at this one. Permanganate MnO4 is actually purple. All right, so let's pick a purple pen. It's purple. All right, and then manganese 2+ is colorless. Colorless. Okay, so let's do a redox reaction. So, okay, so I'm gonna put some permanganate into this vessel. All right, and you'll see that it is in fact purple. I think I just need a little bit. Yes, wouldn't you agree? That is purple. Is that purple? Yes. Okay. So remember, manganese, permanganate, that's the reduction reaction. So this substance will be getting reduced. You can see the purple, right? Yes. Okay. So now to this vial, I'm going to add the other reactant. So the thing that's going to be oxidized, and that is sodium. So in this case, what we balanced was oxalate, but I'm going to actually add sodium nitrite. It's the same idea. It's just a different oxidant. All right. So I think, I don't know how much to add. It says a scoop. Okay. So what color is sodium? The other thing. Yes, it's colorless. Great. Okay. So when a redox reaction happens, permanganate should convert to the colorless, here, I'll put this up there, to the colorless manganese 2+. So what's going to happen when I mix these two things up? What do you think? Yeah, that this purple thing will become colorless. All right, so let's do that. Huh. Why isn't it turning colorless? There's not enough. What else? What else is in the balanced redox reaction? What else is in there? We balance it in blank conditions, in acidic conditions. This is neutral conditions right now. So what I have right here is 6 molar HCl. All right, so I'm just gonna add a little bit of acid and we'll see what happens. So yeah, we'll just see what happens. I have to give it a mix. There we go. So there, did the redox happen? Redox reaction happen? Yes, it did. The moment I added acid. And so that's what it means to be balanced under acidic conditions. Okay, there you go. All right, so I'll see you on Thursday. We'll continue.